This third video is about what people sort of lovingly refer to as voodoo correlations. And this is something that Ed Vull and his colleagues brought to the community's attention quite a few years ago at this point, with a paper that they had produced an interim title of something along the lines of Voodoo Correlations in Social Neuroscience. Ultimately, when the paper came out, it had a slightly different title. But when it was circulating within the community, it had this very contentious title because what they were interested in was that a number of papers that had been published in really high-profile journals had published social neuroscience papers that showed strikingly high correlations between activation in particular brain regions and other measures. Sometimes they were other activation measures, sometimes they were behavioral measures. But one way or another, there were some very strikingly high correlations. Now, anybody who's been in the field for a while knows that correlation's a powerful tool, but correlations above a certain height are unusual. You don't normally get R values that are above 0.8 really. That's a very strong correlation, let alone anything higher than that. And there were several papers that had been published in some of the top journals that showed even stronger correlations than that. So Vull and his colleagues had a look and said, well, what's going on? Why are we seeing these really, really high correlations? And what they noted was that in all of these studies, the correlations come with activation being summarized in a region of interest. So that is to say, you're picking some region of interest and you're not interested in like the activation in this voxel or that voxel. You're just interested in what's happening in this region in general. So for instance, in social neuroscience, theory of mind is one of the big issues. So there are various regions that we know are associated with theory of mind and empathy, that is understanding what someone else is thinking. So one of them is, for instance, within the lateral angular gyrus. So if you were interested in this as a hallmark, as a biomarker of theory of mind processing, you don't really care if it's in this voxel or that voxel. You're going to say, look, within this region, I'm going to summarize the activity there and use that as a biomarker of the engagement in theory of mind. Now, if you had, say, designed an experiment where you had a number of conditions. You had a control condition where there was no sort of theory of mind processing that you would expect. You had something that was very much important to do theory of mind processing, maybe a Sally-Ann test or whatever. And then maybe you created some sort of intermediate conditions with that. Well, one way to define that region of interest would be to say, well, let's look at what's happening in my big theory of mind condition, my Sally-Ann condition, versus my no theory of mind, my control condition, and say, well, what parts of the brain are active? Lo and behold, among other regions, you find activation in this lateral angular gyrus, and you say, okay, well, that cluster is going to be my region of interest that I'm going to use as my biomarker. And now you might then say, well, what I'm anticipating is that activation will go from my control condition up a little bit to my intermediate, like my low theory of mind, to an intermediate theory of mind, to my high theory of mind condition. And if I see that kind of linear increase in activation, that fits my predictions about the theory of mind processing engaged in these various tasks. Well, if you use the ROI that I just described, you're more than halfway there already because you've already defined it to be low in your control condition and high in your high theory of mind condition. So as long as those other two conditions are somewhere in the middle, you're going to get a fairly strong linear correlation. Why? Because the data that you're testing are also the data that you use to define your region of interest. They're not independent of one another. You get this kind of circular logic in the way these things are set up. So if your region of interest and the thing that you're testing are defined on the same set of data, then you create this circularity, you create this inflated type 1 error. Let me see if I can take you through the logic of this. So if you threshold an area to define it as just a region of interest, right? So let's assume that it's got a signal at this level, and that's sufficient to pass threshold. So your threshold's here, you've got some sort of values in terms of your bold signal, and it's above threshold, so therefore it's something you're interested in. One thing to bear in mind there, though, is by definition, whatever you're measuring, this signal, is a combination of signal and noise, right? It's the thing that you're interested in terms of bold signal within the brain, but it's also got all sorts of noise processes added on top of that. In general, the noise that gets included is neither positive nor negative. It's both. You get a combination of it, sort of with a center around zero, and some of it's positive and there's some of it's negative. However, if your signal is just above threshold and you then were adding a significant amount of negative noise, you would actually reduce this activation below threshold. You wouldn't even see it. So as a result, it's safe to say that whenever you're looking at this activation, the noise that's being added into it is either sort of around zero, or if anything, it's positive. So you've got positively skewed noise because you know it's already past threshold. If it were negative, it would have been below threshold. So what we see from that is, by doing that, if this is the true signal, and then you've added positively skewed noise, you can see that the effect size has artificially increased. It's not valid in the sense that there's a difference, but you're overestimating your effect size because of this thresholding procedure that means that you're looking at positively skewed noise values. And that's exactly what Voll and his colleagues were sort of calling out. They were saying, look, there's this process of using the data, using this kind of thresholding to define the sets of regions, and that produces a circularity in these definitions that artificially inflates effect sizes, artificially inflates correlations. So the key thing here is really how you define your region of interest. Now, we've talked about regions of interest. They serve essentially two functions. One is to summarize the aggregate performance within a region, which is what we're talking about here. And the other is really to decrease the number of multiple comparisons that you're doing. We talked about that, for instance, 2 weeks ago, I think, at this point. But it really matters how you define that region of interest. If you do it by looking at your data, then you are artificially inflating the statistical significance of what you're doing, right? Because you're using the data to define what would be the right way to do the thresholding. And that's a bad practice. That's just the wrong thing to do. So what you really need is an a priori definition of your region of interest so that you can say what it is independent of the data that you're actually looking at, so that looking at that data can't consciously or unconsciously influence your definition of the ROI. There are loads and loads of different ways to define a region of interest, right? And I'm just going to give you a sort of a quick thumbnail tour of this. One is that you could do it anatomically. You could say, well, look, I looked at the literature. I know that the angular gyrus is, or at least this lateral part of the angular gyrus is commonly engaged in theory of mind issues. And I can say, okay, well, I can define the angular gyrus. I can see the borders, the superior and inferior borders, the posterior and anterior borders, and therefore I could say this is my anatomical region of angular gyrus. And that's fine because there's nothing about that definition that depends on your data, right? You're referring to existing data, other studies that have shown that the angular gyrus is involved, but that's fine because those data are independent. Those data don't change the data in your study. You can do it functionally. You can do it with independent data. So this is the idea behind functional localizers. So people like Nancy Canwisher and others, who, by the way, was on that Ed Voll paper, Canwisher, would say, well, yeah, sure, you run a functional localizer for 5 minutes. You collect sufficient data to identify your theory of mind region or your face region or whatever it is, the extrastriate body area, etc. And then you run your main experiment. And that's perfectly fine because, of course, those two data sets are independent. Same people, but they're doing different things. There's literally different data, and therefore one can't directly influence the other. Perfectly valid way of doing it. I mean, we talked about some of the shortcomings of that in terms of some of the assumptions underlying it, but statistically, absolutely nothing wrong with that. If you do it anatomically, there are multiple ways of doing it. You can do it via macroanatomic landmarks, you can do it via sulci and gyri, etc. And that's kind of the way I implicitly suggested in my definition of angular gyrus. But you could do that manually from each participant, right? And that is going to be your gold standard. If that's what you think is relevant, that it's going to be angular gyrus, well, then you need to identify each of those landmarks in each of your participants and make sure you identify the angular gyrus in those subjects. You then might look for the area of common angular gyrus across people and use that as your definition for your group analysis. But you've done it painfully and in detail, but absolutely correct across your individuals. You could also do it probabilistically. You could use something like the Lonnie Atlas or the Oxford Harvard Atlas and say, well, we know that, we could set a threshold. We could say, look, if it's 70% likely to be angular gyrus, we're just going to keep all those voxels. Or you could say, whatever threshold you want. But you could define it, and again, it's a priori and independent of the functional data that you've collected. So years ago, I was doing some work on perirhinal cortex, and there was no definition of perirhinal cortex, and I can't remember the actual number of subjects that I did, but what I did at the time was just looked at what felt like an infinitely large number of scans and manually delineated perirhinal cortex according to existing anatomical criteria, and then warped everything into standard space and created probabilistic maps on that. Loads of groups have done things like that. So there are probabilistic anatomical definitions, maps, that are almost all freely available in case you're interested. The other thing that you could do is you could use a single subject template. You could say, well, I'm going to just use the AAL definition of the angular gyrus. So if you recall, this is the automated anatomical labeling atlas that was done based on the Collin brain. So you could look and use Collin's angular gyrus. For all the reasons I've talked about previously, I don't think that that's an awesome choice because Collin wasn't in your study. And Collin certainly wasn't all of your participants. So you can do it. It's unbiased, so it's fine. But I just don't think that it's as valid as you could get if you actually put a little bit more work into it and did it using either a probabilistic method or manually delineating it across all of your participants. Probably the most common way people do it is they pick some coordinate from some previous study and say, well, look, this is the peak coordinate of some theory of mind study that I ran previously or that some other group ran previously. And all I'm going to do is draw like a little sphere around it or a cube around it and say, well, that's my region of interest. And that's fine if you didn't look at your data first. If you looked and said, well, where in angular gyrus am I getting activation? Okay, now where do I find other theory of mind papers that have found activation that's near that? That is circular at that point, right? You are looking in the area where you already know you have your answer. So that's something to avoid. But if you've done it a priori, and in particular, this is one of the benefits of sort of meta-analysis. So you're not picking perhaps a single study, but you're saying, like, look, across studies that have looked at theory of mind, we can say that there's some consistent activation in this area, and therefore I'm going to use that as my region of interest. That's totally fine. And when you do that, you can either define a set of regions. You could say, well, I'm going to go from X from, A to B, Y from C to D, and Z from E to F, and create a region. Or you can just pick a single voxel and draw a sphere or a cuboid around it or something along those lines. But whatever you're doing, it needs to be independent of the data that you've already collected for your experiment. And then just to review, so that was anatomical. In terms of functional definitions, we have essentially two choices. If you're going to use independent data collection, a la Canwisher and Rebecca Sachs and others, then that's totally fine. Just run a separate little experiment with those individuals that allows you to define your region of interest and use that in the main experiment that's a separate set of data. The alternative is the sort of Carl Friston, Rick Henson approach, which is to define a factorial design where your factors are orthogonal to orthogonal to one another. And in that case, you can use the fact that they're orthogonal, that is to say independent, in order to define them. So B doesn't determine whether you're more likely to be an A1 or A2. As long as you know that those are orthogonal, they're independent, then it's perfectly valid to use the same set of data because it meets this independence assumption. And that is only going to be the case if your design was set up so that those factors are orthogonal. And then the last thing I want to mention is just how important is it that you're careful about the size of the ROI. So as the size of the ROI increases, so does the heterogeneity within the region, right? So if you're using it to summarize the activity of an area, then the more heterogeneous it is, the less meaningful that summary is, because there's lots of different functional units in there that are perhaps doing independent things, and then lumping them all together into one thing probably just dilutes the signal that you're interested in which case you probably want a smaller, more focused region of interest in that case. On the other hand, if you're using the ROI to reduce the number of statistical comparisons that you're doing, and you're using cluster statistics, that heterogeneity is absolutely essential for the cluster statistics assumptions to be met, right? If it's too small, there aren't enough results in there, then you don't get a good empirical estimate of the null distribution of your cluster sizes. And as a result, you can't meaningfully determine what the correct threshold is for a significant size cluster. So there's pluses and minuses here, and it depends on what you're using the ROI for. But the critical thing, and the way to avoid voodoo in your fMRI, is to make sure that whenever you're doing any kind of ROI analysis, you are doing it based on an ROI that is independent of the data that you're doing it on. If it's not, then you need to take a long, hard look at how you define that ROI to make sure that whatever you're doing, it's not artificially inflating the effect sizes or the correlations or whatever it is, and producing what we now all lovingly refer to as voodoo correlations.